So we've been introduced to the move structure and we've seen how it worked. But this lecture, I want to also make a point about why in practice it might be preferable to use the move structure compared to other compressed indexes. And this is going to have to do with its use of memory and how fast it is. So when we initially motivated the move structure, we did so by bringing back up the bounds that were achievable with the R index. For example, if we're going to do a count query for a length m pattern, then we'd have a trade-off, right? We could either achieve big O of m time and then slightly worse than big O of r space, or we could achieve big O of r space but slightly worse than big O of m time, whereas the move structure achieved best of both worlds, big O of m time, big O of r space. That was the initial motivation. But there's another separate motivation for why we might prefer the move structure over the R index. And for that, let me just refer back to the R index and let's just recall what the R index is made up of. It's made up of a lot of stuff because if you really look at each of the data structures that we need to query in the inner loop of the R index, you tend to see a kind of nesting pattern where one data structure actually consists of several other data structures, and then those in turn have even smaller constituent structures. So for example, let's just take a rank query in our index world. Like one of the things that we need is the wavelet tree built over the run length compressed string S. A wavelet tree in turn is a tree of bit vectors over which we have to be able to do rank select and access queries. And then in order to do rank select and access queries, or even just rank queries, on a bit vector, we need additional data structures, right? We might need like the Jacobson's rank data structures to do constant time rank queries, etc. So my point is the R index inner loop requires that we access different bits of memory all over the place, right? Like different data structures, different tables, all in different parts of memory. It's got a very kind of wide, unpredictable, disparate memory access pattern. Okay, and I'm just trying to zoom in on one example, but we need to do much more than just the rank queries on S, right? We need to be able to do predecessor queries. We need to be able to do the locate queries, which in turn require predecessor queries, blah, 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 blah. There's many, many data structures involved. When we do lots of disparate memory accesses to different parts of memory in the inner loop of our algorithm, that has implications for how fast the algorithm can be. So just thinking about how a computer is organized, the place where the work is done is the processor, which I have denoted with this sort of brain icon down here. And then the larger data structures, like for example, if you were to build a move structure over many human genomes, that would be a big data structure. It would have to live in memory, right? And if the data structure was much bigger than that, it might even have to live on disk or a solid state disk or something like that. But usually we manage to build pangenome indexes that we can fit into physical RAM. But they don't fit in the closer levels of the memory hierarchy. They don't fit in the cache. And so the processor, when it goes to use data so it can execute its instructions, most of the time that data is nearby and available because it's a typical memory access pattern is usually accessing other memory that was also accessed recently, right? So if memory was accessed recently, we tend to have it in our cache sort of nearby. Whereas in an algorithm that goes to many different places in memory, sometimes it's more typical that it won't be available in cache. I'm using a kind of visual analogy on this slide. If you're in the library and you are studying and you need some books to do your studying, maybe what you would do is you would first look up where those books are, bring those books back to your desk, and now you can read those books and switch between those books and study those books. And it doesn't take long to switch from book to book. But if you suddenly find that you need a new book, right, you have to track down one of the references in the book that you were just reading, and it's not on your desk, well, now you have to go back to the library, right? Maybe you go back to the card catalog and look up where this book is located, and then you go to the shelf, and then you scan the shelf, and then you find the book. The point being that takes a long time, relatively speaking, right? So if we can make use of the cache memory, if we can make maximal use of the books that are on our desk, we save a lot of time that we would otherwise have spent going to and from the library's shelves. Okay, so if the data that our algorithm is using was used recently, or it's near some of the data that we were using recently, an interesting special case of this is if you're accessing memory sequentially. If you're accessing memory sequentially, the hardware is usually clever enough, right? The computer hardware is clever enough to notice that you're doing that. And it's saying, oh, I see, this person is just walking through memory in order. I should go fetch ahead, right? Like I should go fetch the memory ahead of where they're looking so that it's ready for them by the time they get there. So if the data that you're accessing was actually accessed recently or is near other data that was accessed recently, then usually you don't have to wait for it to be retrieved from main memory. It's usually already in the cache, and that would be called a cache hit. When the data you need was not accessed recently and is not present in the cache, or it's not near anything that you accessed recently, it's probably not in the cache, in which case you have to go out to main memory, and that takes time. Similarly to how it would take time to look up and then go find a book and then go get a book in the library. In a processor, the difference between these two, the difference between a memory access that hits in the cache and a memory access that misses in the cache and has to go to the main memory, is a lot, right? So accessing the closest levels of the cache, usually call this the L1 cache. That's the closest cache. It's also the smallest cache, and it's very close to the processor. It takes on the order of a few nanoseconds, right? So a few nanoseconds is not a big deal in microprocessor time. Microprocessors these days, at least, are usually clocked at around 2 to 3 gigahertz. 3 gigahertz means you can do 3 things per nanosecond. So waiting a few nanoseconds is not a big deal. You're not missing out on your ability to do much work. However, when you have to go all the way to main memory and retrieve a bit of data, and you can't proceed with your algorithm until you have retrieved that data, then you have to wait potentially closer to 100 nanoseconds. Right? It sort of depends, right? It depends on whether that data happens to be present in some other level of the cache hierarchy. But let's just say if you have to go all the way out to main memory, usually you're paying something like 100 nanoseconds of time that you have to wait. And that's a bigger deal because, again, let's assume the processor is clocked at 3 gigahertz. You could have done 300 things in that time that you're spending waiting for the memory to be fetched. Okay, so an algorithm that doesn't have to wait like this very much, some amount of this waiting is usually unavoidable, especially if we're accessing a large data structure like an index. Okay, so some amount of waiting is unavoidable, but an algorithm with a minimal amount of such waiting, where usually our memory access patterns are such that we are accessing data that we used recently and that is in the cache, right? If that's the case, then we would say the algorithm has good locality of reference, right? So when it references memory, it tends to reference it in a way that's cache friendly. It's either referencing something that it already referenced recently or that's nearby. So returning to the point we were making earlier, our other criticism of the R index might be that it does not have good locality of reference. Because its inner loop has to navigate several data structures, maybe a Jacobson's rank index 4-bit vector in a wavelet tree, and maybe six other Jacobson's rank structures just like that for different bit vectors in the same wavelet tree. Because we are doing all these disparate accesses, we have poor locality of reference. And for that reason, we have lots of cache misses. And cache misses mean we spend lots of time waiting for data to be retrieved from main memory when we could have been doing something productive. And just a quick aside, you might, if you have programming experience, you might think of multi-threading as a way that we sometimes get away from having to wait for long periods of time without doing any useful work. For example, if we're reading data from a disk, it could be useful to have multi-threading because when one thread is reading, it can while it's waiting for the data to be retrieved from the disk, it can essentially go to sleep. It can become suspended by the operating system, and then the operating system can schedule another one of your threads to run in the meantime. But that doesn't work here, right? These sorts of memory access pauses, these cache misses, they're not substantial enough to give the operating system a chance to suspend the thread. They're sort of finer grained than that. You really do just wait, right? Your thread stays scheduled on the processor, but it does nothing for a while, waiting for that memory to be retrieved. Okay, quick reminder. In the move structure, we want to contrast the move structure now with the R-index with respect to its memory access patterns. So let's just remember what happens in an iteration of a query of the move structure. Well, basically we do two things. We sort of like compute our new k prime. That's real quick and easy. Then we compute what might be our new I prime, except we might be a little bit off, right? So we compute our new I prime by just retrieving the xi field from row I. We then jump there. We might not be in the exact right place yet. Like in this example, we jumped here to run 9, but we weren't quite in the right place. We needed to be here, so we had to jump 2 runs forward, right? So we had to do 2 forward scans. We also sometimes call these fast forwards to get to row 11. Okay, so we had to do the bigger move to get to the new row I prime, or at least our initial guess for what I prime should be. But then we also had to do these smaller adjustments, linear scans, to get to the row with the correct I prime. Okay, let me just show that in pseudocode form. I actually haven't showed this yet in the previous lectures. So here's some pseudocode that does everything that we need to do in a step. We first compute the new k prime. That part's easy. We then compute a initial new I prime. This is not yet the correct I prime, but it is sort of the first place we land when we're trying to compute I prime. And then we iteratively look for the row that really does contain the k prime that we are jumping to, at which point we know we'll have the correct I prime. And we have to increment I prime every time we skip a row. We return k prime I prime. Okay. The point being, the memory accesses in this algorithm are really of two kinds. There's the first time we have to access a new row in the move table, a row that is different from the row that we're currently in. It's sort of like basically the first time we get to here, right? When we access m of I prime dot p and m of I prime dot l. That I prime is a new row. It's different from the row that we were just in, right? It's different from I, right? I prime is different from I. So that's like a large movement through memory, potentially, right? The row that we jump to could be very distant from the row that we began at, right? So these memory accesses, the first time through this while loop, will be to a new distant place that will almost certainly, if our index is very large, then this place has a low chance of being in the cache. It's probably not in the cache, it's probably in main memory. So the first time we hit one of these dereferences, where we were looking into row I prime in the move structure, that should be a cache miss most of the time. However, we then do these subsequent iterations, right? Because if the first place we land isn't the correct place, we have to scan forward a little bit. And as we're scanning forward, well, these are predictable memory accesses because, again, they're close to the row where we originated, right? If we begin at a certain I prime, then we increment I prime, increment I prime, increment I prime. That's us walking through memory in a sequential fashion. So those are more predictable. There's a better chance that the underlying hardware in the computer is doing our job for us by fetching ahead, finding the memory that we need in future iterations and grabbing it before we need it. And what you see on the screen right now is basically the whole story, right? Like the querying the move structure is very, very, very simple, right? It's not like there's very complicated data structures behind what you see on the screen right now. M is just a table, right? M is just, you can think of it as an array of structs or something like that. It's just a tabular data structure, very simple. It's not like behind the scenes there are wavelet trees and bit vectors. It's really just a table. So we can really look at this algorithm and see quite clearly where the memory accesses are We can see where the tricky one is, and we can see where the not so tricky ones are. Okay. So if you just picture what the memory accesses are like if we go through the process of matching a query, we know, of course, that we're going to do repeated LF steps. So we're going to call this pi function repeatedly, right? Each pi is one LF step. So we're going to call this repeatedly, okay? So if we just picture this like in terms of the clock hand moving and what are we actually spending time doing, a disproportionate amount of our time is spent waiting for that first memory access to be resolved. Okay, so now I've drawn the red box taller than the blue box. So it's good news that only some of the memory accesses are slow, but ideally, we would even like to reduce the negative impact of those slow memory accesses. Is there some way we just can do something else useful instead of just waiting for 100 nanoseconds for that memory access to happen? We can using something called prefetching, memory prefetching, or sometimes people call it software prefetching to contrast it with the kind of prefetching that the computer architecture will do for you automatically. So you can actually write into your program a statement that says, oh, please go preemptively fetch this address from memory. And, a little bit around it. Usually you fetch about 64 bytes worth of memory at a time or something like that. Go fetch this address in memory. It happens asynchronously. So in other words, when you issue this prefetch instruction, it doesn't make your program stop, right? Your program can continue. And if what you do is you do something like 100 nanoseconds worth of work, then go back and try to use that memory that's at that prefetched address, hopefully it's already ready for you, right? So the point of doing this asynchronously is that if we had done it synchronously, then the moment we asked for the memory, we would be stopped, suspended, frozen, waiting for that memory to be retrieved. And all that time while we're waiting is not being used for any useful work. Whereas if we issue this prefetch instruction asynchronously, then we go about our other business. Maybe we have some other computations to do that don't really require that memory, right? We've got some other small things to do, some arithmetic over here. Then we can make use of that time that we would otherwise have just been paused. Okay, so for example, if I bring back this diagram again, that is trying to show sort of the memory access pattern over time and what actually takes time, right? The cache misses come from the distant memory accesses. So the first time we access m of I prime. Then we have a little bit of fast forwarding work to do, and that's not a lot of work, but it's some work. And we can perhaps do that work while we're waiting for the distant memory to be retrieved. So one idea would be, once we know what's the next memory address we need to retrieve, in other words, once we've retrieved m of I prime, we can go ahead and start preemptively prefetching the next xi, right? The next ID that we're going to go to. And while we are waiting for that prefetch to finish, we can do some other work. And as a result, that distant memory comes in and lets us continue with our work a little bit quicker, right? So we might hit that next point where we would have had a cache miss. We still, because we probably didn't use 100 nanoseconds here, right? This is only, 10 nanoseconds. So we only used about 10 nanoseconds of that 100 nanoseconds pause, and then we had to pause again, but now maybe we don't pause for quite as long because the prefetch had already put in motion the movement of that data from main memory. So, in this example, we used memory prefetching and maybe we got a little bit of benefit from it because we did some work while we were waiting. But in this example, we didn't do very much, right? That near rectangle is not very tall, indicating this isn't nearly as long as the latency of a cache miss, right? The amount of time we have to wait for a cache miss. So we saved some time, but maybe not a lot. So here's one more idea just to show that we really can hide this latency, most of it, if not all of it, a lot of the time. So let me just remind you that when we are querying these indexes, we're usually not just doing one pattern, right? So in the world of genomics, which is the world I live in, we usually have many, many, many patterns that we are going to use to query this index, right? So this move structure index is a compressed index structure that we are going to query with many, many, many patterns in another loop, in sort of our outermost loop is going to be a loop over these patterns. And so the idea for how to hide even more of the latency is that when we have an opportunity to do some work in the meantime while we are waiting for something to be fetched from main memory, we can shift to another query. We can sort of interleave the processing of multiple queries so that once the processing of one query has to wait for a while, we immediately just switch to another query and make a little progress there. And maybe go to a prefetch and then switch to yet another query. So in terms of my diagram, that might look like this, right? We issue our prefetch as soon as we sort of know what is going to be the next row that we are going to need after the one we're processing currently. We maybe do a little bit of that near work in the meantime. Maybe we do our fast forwarding and some other arithmetic. Now we're finished. Like there's no more work for us to do to occupy us between now and when the memory is finished being prefetched. So rather than just pause and stall until that prefetch finishes, we switch to another query. Like maybe we're in the middle of a match query for another sequencing read. We just switch over to that one and make a little progress on that matching process. Again, till we get to the point where we've issued the prefetch and we've done all the work that we can do in the meantime. So we switch to yet a third query and so on, right? So if we just keep switching between the queries, then our hope is, if we design this right, we have to design it just right where we pick the right number of queries, for example. And we hopefully have a pretty good idea of how long this pause is due to the cache miss. But if we design everything just right, then frequently when we switch to a thread, when we switch to a new query, that query's prefetched memory is already available. So with this idea, we can take the biggest advantage of the move structure, which is that it doesn't touch lots of disparate data structures. It only really uses this one table. And even though some of those memory accesses are still of the sort of long distance and unpredictable kind that will probably incur a cache miss, even so, we can use memory prefetching to hide the latency of those cache misses. And so in this implementation, and I'm going ahead and showing you a paper that's from my own research group here, we implemented a move structure and we implemented this prefetching idea, and we were able to demonstrate that if you do this trick where you do prefetching and you switch between queries so that you're always keeping busy in the meantime while you're waiting for the memory to be retrieved, then you can have a speed up of more than twofold, right? Which is pretty good, right? It's good to think that even though there is still a tough memory pattern, right, a memory pattern that's not predictable, that you can still get performance that's approaching what you would have got if your memory pattern was much more predictable. Okay? And this takes care of a pretty important criticism that you might level in general against BWT-based indexes. Right? Burrows-Wheeler transform-based indexes tend to hop around in a pretty unpredictable way. This is in contrast to some other indexes that are based on suffixes, like suffix trees or suffix arrays, where you could argue that as you proceed in the process of matching a query, you tend to eventually get to a place where the accesses are sequential or close to sequential. Like if you just picture binary search on the suffix array, once the binary search range gets sufficiently small, at that point you're basically just doing character comparisons with a particular suffix. So it becomes kind of sequential at that point. BWT-based indexes, on the other hand, because of just the huge difference between text order and BWT order, you tend not to have any you tend not to have any sequential accesses, right? Basically, everything you do from iteration to iteration has to move a long distance through memory. And so by using the move structure and by hiding the latency as effectively as possible, we can sort of hedge against what might be the one of the biggest weaknesses of Burroughs-Wheeler based indexes in terms of their speed.